Hi everyone, it's Miss Wong here. This video should be shorter than the other video. We will be going over graph number 2, part of the same practice worksheet number 1. And I just wanted to separate the videos because the other one was getting long and I didn't want you to have to go back and forth between and scrolling in between the time zones of two different graphs. It would take a long time. So let's start by reading off the question. A kid on the roof of a high-rise apartment block throws a ball straight up. It stops for an instant, then falls to the ground. Plot a velocity time graph for the ball data. So the ball data, you must plug it into this graph here, pick your correct ranges, and once you plug it all in, you're going to notice that it forms a straight diagonal line. The straight diagonal line, which we talked about it a lot in the other video, means a constant acceleration, okay? So constant acceleration is what we're working with. Constant acceleration, meaning it is uniform. It's uniform because if you use any of these points to plug into your slope formula, you're gonna get the same number, and that slope that we're calculating for is acceleration. So you're gonna get all the same acceleration values no matter which point you use on the graph. So let's read the first question. How many phases are there in the motion of the ball as illustrated by this velocity versus time graph? Well, there's 2. How do we know that? Because these phases here, right when this line crosses at the x-axis at 0 here, you're entering into a bunch of negative velocities. And that's why we consider S2 to be a separate motion, because now you're going backwards, okay? Even though it's the same diagonal straight line going downwards, it's considered a separate motion. So that's why we have 2. Explain what is happening during each phase in terms of uniform motion. Well, in each phase, S1 and S2 is the same diagonal line, but each phase is having that constant acceleration because the slope is a straight diagonal line. So if we take any of those numbers and plug it into our slope formula for acceleration, we'll get the same values for acceleration, which we'll see very soon once we solve for it. Because question 3 is asking us to solve for acceleration. It's telling us to solve it directly on the graph, but you don't have to because you have this empty white space here. And I prefer if you write it on the white space so that I can see your values better. I'm going to have to take that out next time. Okay, so S1. A with the arrow on top just saying that it's a vector quantity. Acceleration is a vector. It has both magnitude and direction. And that slope formula for acceleration is rise over run. Our rise being velocity, because rise is y over run, which is x. Okay, so velocity over time. So change in velocity over that change in time. Vf minus Vi over T, F minus Ti. We're going to pick points from this line that are obvious, okay? Because you can pick any points you want to solve for acceleration on this S1 line because it's constant acceleration. It's going to be the same no matter which points you use to calculate. However, it's just easier picking definite for sure points, and you can also pick points just using the data here because they give you specific and definite decimal values as well. So we're just going to plug those values in here. So I'm using Vf of 0.2 meters per second minus 12.0 meters per second over 1.2 seconds minus 0 seconds. And that will give us minus 11.8 meters per second divided by 1.2 seconds, which equals negative 9.8 meters per second squared. Because if you go negative 11.8 divided by 1.2, you get a negative 9.8 meters per second divided by seconds. You're actually multiplying these 2 second values to get our squared, okay? So we notice negative 9.8 meters per second squared. We check back at our data to double check if it sounds about right. Well, definitely, because we have a negative value. We know that S1 that acceleration will be negative. So to even triple check our work, we're going to solve for the acceleration of S2 to see if we get the same value because of the straight diagonal line for both S1 and S2 are jointed. Therefore, that acceleration should be the same. So let's solve for S2. Acceleration equals a change in V over change in T equals VF minus VI over TF minus TI equals, and again, we're going to use points on this graph that are definite points, or you can just take it straight from your decimal values here. But again, if you use any of these points to solve for your rise over run for slope, which is acceleration, you'll get the same value. So it doesn't matter if I take these points here or these points here, I'm going to get the same acceleration because it's constant, it's uniform. So I'm going to plug in my points that I decided to pick, and I decided to pick a negative 31.1 as our final velocity minus that negative 1.7 meters per second as the initial velocity, and as my final time I chose 4.4 seconds, which was associated to the 31.1 minus 1.4 seconds, which is associated to the negative 1.7 initial velocity. Okay, and then once you do all those minuses, watch out for this here. Okay, minus with a negative actually turns into a positive because these two signs multiply each other to make a positive. Therefore, you should get negative 29.4 meters per second over 3.0 seconds. Once you divide that over, you get negative 9.8 meters per second squared. Okay, make sure you have the right units because velocity versus time graphs, acceleration will always be meters per second squared. And if we look back and compare our accelerations, S1 equals S2. Look at the acceleration, negative 9.8 meters per second squared, negative 9.8 meters per second squared. So it's the same thing because we thought it was. It's part of the same line that's going down, okay? It's that straight line showing and proving that we have a constant acceleration. So let's answer question 4. What changed directions, the velocity or the acceleration or both? Well, velocity went from going to a positive direction down into a negative direction, and then acceleration was always negative. So was always negative. Sorry, not also, always negative, because we saw that when we calculated for acceleration in segment 1 and segment 2, both were negative accelerations. Velocity, however, did change from positive values down into negative values, okay? The next part, when is the velocity negative? Well, the velocity is negative in S2 there, and S2 kind of starts around 1.2 seconds, okay? That's when velocity starts becoming negative. When is acceleration negative? Well, it was always negative. Always negative. All right, so that solves those questions there. If you still have questions about this graph, send me a message on Microsoft Teams. I wish you best of luck. Make sure to practice. Have a great day.